Dear students, welcome to the unit number 6 of Software Engineering. In the previous unit, we studied what is analysis modeling and how to create data, functional and behavioral models using entity relation diagram. Let us start with what is design. Software design is concerned with deriving a solution which satisfies software requirements. A software design can be traced to a customer's requirements. The designer's goal is to produce a model or representation of an entity that will later be built. The design process. Software design is an iterative process through which requirements are translated into a blueprint for software to be developed. We start the design with high level of abstraction, which means that the initial design represents the entire system. Initial design can be directly traced to specific data, functional and behavioral requirements. As design iteration occurs, subsequent refinement leads to design representations at much lower levels of abstraction. Let us start with abstraction. A modular solution to any problem can take us to many levels of abstraction. In highest level of abstraction, a solution is stated in broad terms using the language of the problem environment. The statement that we want to automate computer science department is an example of high-level abstraction. In lower levels of abstraction, a more procedure-oriented approach is taken. Example of lower level of abstraction is that we identify the processes and functions to be performed by the automation software. In the lowest level of abstraction, the solution is stated in such a way that it can be directly implemented. The example of lowest level of abstraction would be that we write the pseudocode for the individual functions. Each step in the software engineering process is a refinement in the level of abstraction of the software solution. As we move through different levels of abstraction, we create procedural and data abstraction. A procedural abstraction is a named sequence of instructions that has a specific limited function. A data abstraction is a named collection of data that describes a data object. The figure on your screen defines a data abstraction door that encompasses a set of attributes that describes the door. The procedural abstraction open, shown in the figure, makes use of attributes contained in data abstraction door. Number 2. Refinement. Refinement is actually a process of elaboration. We begin with a statement of function that is defined at a high level of abstraction. Refinement causes a designer to elaborate on the original statement, providing more and more detail as each successive refinement occurs, as illustrated by figure. Software refinement is a top-down strategy. A program is developed successively, refining levels of procedural details. A hierarchy is developed by decomposing a macroscopic statement of a function in a stepwise fashion until programming language statements are reached. In each step of the refinement, one or several instructions of a given program are decomposed into more detailed instructions. Number 3. Modularity. Software is divided into separately named components called modules that are integrated to satisfy the problem requirements. It leads to divide and conquer strategy, that is, it is easier to solve a complex problem when you break it into manageable components. A design method can be evaluated with respect to its availability to define an effective modular system. These criteria are used to judge the design method. Modular decomposability. If a design method provides a systematic mechanism for decomposing the problem into sub-programs, it will reduce the complexity of the overall system. Modular composability. If a design method enables existing reusable design components to be assembled into a new system, it will yield a modular solution that does not reinvent the wheel. Modular understandability. If a module can be understood as a stand-alone unit, it will be easier to build and easier to change. Modular continuity. If small changes to the system requirements result in changes to individual modules, the impact of change-induced side effects will be minimized. Modular protection. If an abnormal condition occurs within a module and its effects are contained within that module, the impact of error-induced side effects will be minimized. Families of related systems. The design should have the ability to reuse architectural building blocks. A number of different architectural description languages, ADLs, have been developed to represent the architecture. The majority of ADLs provide mechanisms for describing system components and the manner in which they are connected to one another. Number 5. Control hierarchy. Control hierarchy is also called program structure. It represents the organization of program components, modules, and implies a hierarchy of control. Different notations are used to represent control hierarchy, but most common is the tree-like diagram that shows hierarchical control for call and return architecture. In a tree-like diagram, depth and width provide an indication of the number of levels of control and overall span of control, respectively. Span out is a measure of number of modules that are directly controlled by another module. Span in indicates how many modules directly control a given module. Number 6. Structural partitioning. The program structure should be partitioned both horizontally and vertically. Horizontal partitioning defines separate branches of modular hierarchy for each major program function. Control modules are used to coordinate communication between and execution of program functions. The simplest approach to horizontal partitioning defines 3 partitions: input, processing, and output. Horizontal partitioning results in software that is easier to test, maintain, and extend, and propagate fewer side effects. Vertical partitioning, often called factoring, suggests that control and work should be distributed top-down in the program architecture as shown in figure. Top-level modules should perform control job and do little actual processing. Modules that reside low in the architecture should be worker, performing all input, computation, and output tasks. Vertically partitioned architectures are less likely to suffer from side effects of the changes and therefore are more maintainable. Number 7. Data structure. Data structure is a representation of the logical relationship among individual elements of data. Data structure dictates the organization, methods of access, degree of associativity, and processing alternative for processing. Organization and complexity of data structures depend upon the skills of the designer. Number 8. Software procedures. Software procedure focuses on the processing details of each module individually. Procedures must provide a precise specification of processing, including sequence of events, exact decision points, repetitive operations, and data structures. Number 9. Information hiding. Concept of information hiding suggests that modules should be specified and designed so that procedure and data contained within a module is inaccessible to other modules that have no need for such information. Information hiding improves software maintainability and reduces error propagation. Let us move to our next topic, that is effective modular design. Functional independence is a direct outgrowth of modularity. Functional independence is achieved by developing modules with single-minded functions. Functional independence is measured using two qualitative criteria: cohesion and coupling. Let us see what cohesion is. The cohesion of a component is a measure of the closeness of the relationship between its elements. That is, it is the degree to which a module performs one and only one function. A component should implement a single logical function or should implement a single logical entity. There can be 7 types of cohesion. Number 1. Coincidental cohesion. Number 2. Logical cohesion. Number 3. Temporal cohesion. Number 4. Procedural cohesion. Number 5. Communicational cohesion. Number 6. Informational cohesion. And number 7. Functional cohesion. Number 1. Coincidental cohesion. A module has coincidental cohesion if it performs multiple, completely unrelated actions. This type of cohesion arises as a consequence of rigidly enforcing rules, such as every module consists of between 35 and 50 executable statements. Modules with coincidental cohesion suffer from 2 serious drawbacks. Such modules degrade the maintenance, both corrective and enhancement. These modules are not reusable. Example of coincidental cohesion could be a module named print next line reverses the string of characters comprising the second argument, adds 7 to the 5th argument, converts the 4th argument to floating points. Number 2. Logical cohesion. A module has logical cohesion when it performs a series of logically related actions, one of which is selected by the calling module. There are 2 problems when a module has logical cohesion. Interface is difficult to understand. The code for more than one action may be interconnected, leading to severe maintenance problems. Example of logical cohesion could be a module performing all inputs and outputs. Number 3. Temporal cohesion. A module has temporal cohesion when it performs a series of actions related in time. That is, all the actions in the module must be executed within the same span of time. Modules which have temporal cohesion are difficult to maintain and reuse. Example of temporal cohesion could be a module named Initialize, which performs all these actions. Open old master file. Open new master file. Open transaction file. Open print file. Initialize sales district file. Initialize global variables. Number 4. Procedural cohesion. A module has procedural cohesion if it performs a series of actions related by sequence of steps to be followed by the product. Such modules are unlikely to be reused. Example of procedural cohesion could be a module that performs the actions read part number from database, update repair record on maintenance file. Number 5. Communication cohesion. A module has communication cohesion if it performs a series of actions related by a sequence of steps to be followed by the product and if all the actions are performed on the same data. Module with communication cohesion cannot be reused. Example of communication cohesion could be a module which updates records in database and writes it to the audit trail. Number 6. Informational cohesion. A module has informational cohesion if it performs a number of actions, each with its own entry point with independent code for each action, all performed on the same data structure. A module with informational cohesion is essentially an implementation of an abstract data type. Number 7. Functional cohesion. A module that performs exactly one action or achieves a single goal has functional cohesion. A module with functional cohesion is easy to maintain, easy to reuse, leads to fault localization, easy to extend. Example: calculate sales commission, write to disk. Let us see now second functional independence criterion, that is coupling. Coupling is a measure of the relative independence among modules or a degree of interaction between two modules. There are 5 types of coupling. Number 1, content coupling. Number 2, common coupling. Number 3, control coupling. Number 4, stamp coupling. Number 5, data coupling. Number 1, content coupling. Two modules are content coupled if one directly references the contents of the other. For example, module P refers to local data of module Q in terms of some numerical displacement within Q. Number 2, common coupling. Two modules are common coupled if they both have access to the same global variables data. Therefore, instead of communicating passing arguments, modules can access and change the values of global variables. This form of coupling is undesirable for a number of reasons. It contradicts the spirit of structured programming. Modules can have side effects. If a maintenance change is made in one module to the declaration of a global variable, then every module that can access that global variable has to be changed. Furthermore, that change must be consistent. common coupled modules are difficult to reuse. As a consequence of common coupling, a module may be exposed to more data than it needs. Number 3. Control coupling. Two modules are control coupled if one passes an element of control to the other module, that is, one module explicitly controls the logic of the other. Therefore, two modules are not independent. For example, control is passed when a function code is passed to a module with logical cohesion. Number 4. Stamp coupling. Two modules are stamp coupled if a data structure is passed as an argument, but the called module operates on only some of the individual components of that data structure. For example, module P passes an employee record, employee number, employee name, basic salary, and module Q uses only basic salary to calculate commission of that employee. Number 5. Data coupling. Two modules are data coupled if all arguments are homogeneous data item. That is, every argument is either a simple argument or a data structure in which all elements are used by the called module. For example, function display time of arrival taking flight number as argument. Design heuristics for effective modularity. Evaluate the first iteration of the program structure to reduce coupling and improve cohesion. Attempt to minimize structures with high fan-out. Strive for fan-in as depth increases. Keep scope of effect of a module within the scope of control of that module. Evaluate module interface to reduce complexity and redundancy and improve consistency. Define modules whose function is predictable but avoid modules that are overly restricted. Design modules which have high cohesion and weak coupling. Design model. The figure on your screen shows the design model. At the base of design model is the data design, architectural design interface design, and procedural design complete the design model pyramid. Each of the elements of the analysis model provides information that is required to create a design model. In the data design, data structures are created that will be required to implement the software. Data dictionary and ERD are the basis for data design. The architecture design defines the relationship among major structural elements of the problem, the design representation. A modular framework of a computer program can be derived from analysis models and the interaction between subsystems defined within the analysis model. During architecture design, generally subsystems are identified and a framework for subsystem control and communication is established. The interface design describes how the software communicates within itself to systems that interoperate with it and with users. An interface implies flow of information, data control. Therefore, the data and control flow diagrams provide the information required for interface design. The component level or procedural design transforms structural elements of the program architecture into procedural description of software component. Information obtained from PSpec, CSpec, and STD serve as the basis for procedural design. Let us move on to our last topic, that is design documentation. Design document usually contains these sections. Number 1, Introduction and Scope. Number 2, Data Design. Number 3, Architecture Design. Number 4, Interface Design. Number 5, Component Design. Number 6, Requirement Cross-Reference. Number 7, Unit Testing Guidelines. Number 8, Design Constraints. Number 9, Supplementary Data. Introduction and Scope section contains the scope and introduction to the problem. The information in this section is taken from the corresponding section of the SRS.